Thank you all for coming today, and thank you, DBT, for hosting this event. Jake and I are here from Drizly, the leader in the alcohol delivery space. Today, we'll be talking about how Drizly uses geospatial analytics to get hyperlocal insights out of market level data. I'll first go through a quick case on capacity limits and utilization, and how we've started using DBT, Mapbox, and Looker to visualize our geospatial data. Then Jake is going to walk us through how he built the underlying geospatial engine, and then give us a bit more context on our stack and geospatial DAG. If you're not familiar with Drizly, we're an alcohol delivery platform that operates by facilitating orders that are then delivered by local alcohol retailers. Stores cover a designated area using a custom polygon that denotes which addresses they can service. When store polygons overlap, a user in the mutual area can shop from both of those stores as long as they're online. One way we monitor network growth is with a simple count of active stores. Within a single market, it's a useful number to keep in mind, but it doesn't tell us about our consumer coverage because these stores don't cover the same exact area. Some users might see 3 of these stores, but others will see 2, 1, or no stores if they fall outside the polygon boundaries. Saying we have 5 stores in this area doesn't really tell us the full story of our local coverage. The data needs to be more granular in order to be actionable. Because we aim to give consumers a uniformly great delivery experience, despite shopping in different states from different stores, each with their own regulations and operations, we can only achieve success on the macro scale by succeeding hyperlocally. As a result, geospatial questions are foundational to our business. As a delivery platform, Drizly is one of the companies that saw significant growth as a result of the pandemic. Once delivery was accepted as the safest option for most people, awareness of Drizly spread quickly, perhaps a little too quickly, because for the first time, stores were often receiving more orders than they could realistically deliver. In late March last year, the mayor of Denver announced that liquor stores would be closed for a few weeks due to the pandemic. As you might expect, there was a mad rush on alcohol that day, including on Drizly. This is a picture taken outside Argonaut, which is one of our Drizly retailers in Denver, looking at a line that goes around the building. The mayor ended up amending the statement so that liquor stores would remain open, but we'd already received hundreds of orders for the same stores that were busy dealing with in-store traffic and didn't have the stock or the staffing to fulfill them all. You can see here the massive spike in voided orders we saw that day. In response, we built a DBT model that calculates the maximum number of orders that will allow a retailer to receive each hour. When DBT runs, the model output is exported into S3 and immediately collected by an engineering job that feeds into the main site to set these capacity limits. We then analyze the day's performance and calculate new limits the next time DBT runs. This is a BI job that directly impacts our bottom line because it controls the upper bound of orders that we can receive. So it's important that the DAG has data integrity tests so we don't prevent ourselves from receiving any orders. Jake will have better diagrams to show you, but this is the basic daily cycle for capacity limits. With capacity limits, we now know the maximum number of orders that Drizly can receive on a given day. Due to the overlapping polygons, when one store hits capacity and can no longer receive on-demand orders for that hour, demand is redirected to nearby stores. If there are no overlapping stores in an area, users temporarily get scheduled-only service. When we layer orders per store over their hourly capacity, we can calculate capacity utilization. And this can be scaled up to look at utilization across cities or our entire network during peak hours. We ran a recent analysis on some of our top cities and found vastly different utilization rates. These 2 cities, I had to scrub the data for anonymity, but they actually have very similar order volume. But because one city has many more stores, supply outweighs demand and utilization is low. Capacity utilization data can help the sales team identify markets with high utilization that need more retailers, and it can also help marketing identify areas with low utilization that need more users. But like we saw with the polygon map, a single value per city isn't enough to pinpoint the right areas that we should be targeting. Jake will walk us through the underlying tools shortly, but I wanted to first show you how we can target exact areas using geospatial data. This is a map from Looker showing a snapshot of capacity utilization in New York City, which we consider to have great coverage using the count of stores metric. But for the first time, we're able to see exactly where we're hitting capacity 6 times faster than the rest of the city. And to bring it back where this all began, let's take a look at capacity utilization in Denver. This is a map of current utilization during peak hours. As Drizly preps for growth, we want to see which areas would hit capacity as order volume increases. So we can use this data to model demand growth at 20% more orders, at 40% order volume increase, and finally at 60% order volume increase. We can see exactly which areas down to the neighborhood are at the highest risk of hitting capacity as we increase demand. And now I'll send it over to Jake, who's going to talk through the underlying geospatial engine that powers this.
Thanks, Athena. Let's see. Can you all see my screen? Right on. Okay. Athena walked us through how the geospatial data is getting used. And I want to talk through how that got built and what undergirds that. And so I think the first thing to go through is just what is a geospatial index and kind of why does that matter? Specifically, what a geospatial index is something that maps a location to some representation, usually a string or some sequence of bytes that have properties that we like. So in our case, we're using Uber's H3 index, which is based on hexagons to cover the entire world in a regular set of polygons. Uber built this to handle delivery and perform analysis. And it has a lot of properties that we like. Specifically, as you can see in this table on the right here, if you look going from left to right in that table, there's H3 resolution, which decides the size of the hexagon you're working with. And you can see there are associated metrics with each one of those. And one thing I want to call out specifically is that rightmost column, number of unique indexes. This is from their documentation. I think it should be indices, but at each layer up, it increases by roughly 7 to 8 times because there is lineage with the hexagons. Based on the string representation, so you can see in the bottom left, the bottom point in the text on this slide, shorter prefixes contain their children. So you can imagine that an H3 index is a string of characters. If you look only at the first 7 characters, those first 7 characters will contain every index that shares that prefix. And so what this does is it encodes locality in something like a lexicographic sort, which is really great for databases. Moving on. What we wanted to do was take those indices and embed them into our systems in a way that analysts can use them and that data science in production can use them. And so this is a list of the tech stack at a very high level that we combined in order to enable this. Specifically, we democratize H3 via a really nice pipeline in dbt that goes into Snowflake. And then we connect Mapbox, Snowflake, and Looker together to unlock visualizations. And I'm going to walk through what that integration looks like. So to talk about what we're actually trying to do, in Athena's slides, you saw a lot of those visualizations where there is a lot of locational specificity to what's happening in deliveries. And she showed the polygons that we have defined by stores, and she showed these really nice grids. And so what I'm going to walk through right now is how do we go from this polygon on the bottom left here to the tiled polygon, sorry about the contrast there, but this tiled polygon on the bottom right, where we're embedding the exact same information, but being able to speak to within the polygon what is happening with comparable units. We want to be able to say that we want to be able to make statements about areas and be comparing the exact same size areas when we do. These services combine a ton of those technologies I talked about, and we're going to look at that diagram in the top right in a little more detail now. This is a workflow that enables analysts to generate new tilings at scale. So if you recall that table I showed with the unique indices, actually, I'm going to go back real quick. Sorry to do this. But one thing I want to call out in this table is you see the number of unique indices gets really big, really fast. And what we are creating are polygons. And so this number of unique indices is how many there are covering the entire world. You can imagine how working with a data set of even 33 billion polygons becomes pretty unworkable pretty quickly. And so it's important that we identify as Drizly, we don't need to have tiling representations in countries or continents where we don't operate. We don't need tiling in the Pacific Ocean. And that's a lot of the area. And so we want to strip that away where we can to increase the speed with which queries execute. So I'm going to go back forward again. So what this task is doing is allowing our analysts to choose the areas that they look at. And essentially what was built is something that all through AWS, because Drizly is an AWS shop, is something that combines H3 with our Snowflake stack and writes it in a format where Looker can access it. The reason it's important to do this for Looker is, again, going back to that scale issue, Looker exposes native GeoJSON and Polygon processing. The challenge there is that Looker loads everything into memory in the browser. And again, coming back to those billions of polygons, you can imagine how loading a 10 gigabyte or 100 gigabyte file into a single browser window wouldn't work. What Looker has set up is hooks to make an external call to Mapbox, who I'm sure many of you have heard of, but Mapbox serves vector tiles. They do a lot more than this, but in our context, they serve vector tiles at scale and are really performant and have a lot of bells and whistles around that. They are able to surface and respond to queries for just a specific area and return just the polygons that you're looking at in your viewing window. And that's really nice for performance. And the only requirement for those queries is that you have something called an extents file, which maps polygons, like arbitrarily shaped polygons, to regular rectangles. So what we've built here is a process by which our analysts can log into the AWS console, write an arbitrary query in Snowflake to pull any polygons that they want, and it kicks off this task in ECS, which takes that polygon, converts it into the regular tiling that you saw, those hexagons, and writes it to S3 so that it goes into Snowflake for our database, writes the extents into CloudFront so that Looker can access it at runtime, and then uploads that tile set in a nice format to Mapbox so that when Looker does make a request to Mapbox, it gets the result that it wants. Cool, moving on. On top of being able to generate the tiling, one thing that we need to unlock as well is the ability of our analysts to work dexterously with the geospatial data. So it's not enough to just say that we have these polygons in Snowflake. We need to be able to make statements about who's in the neighborhood of this polygon, how big is it, what's the parent of this polygon, how many children does this polygon have, if that makes sense. And you can see on the bottom, we have a visualization of the get neighbors function that Uber in their H3 package exposes natively, which is we take this central polygon on the bottom left and we say, give me everything around that. And then we have this ring of polygons and we say, give me everything around that. And what's really nice about that is you can imagine making like algorithmic searches of areas to figure out what's the best area for us to move into? The way that we unlock all of that is with that diagram in the top right, which is Snowflake has external functions. You connect them to an API gateway, and you can define the external functions within a Lambda. And really the only requirement for that Lambda is for every row that you send to the Lambda, for every row that Snowflake sends to the API gateway, it needs to get a result for that row. It's quite powerful what you can do with that, as long as you're very thoughtful about what that Lambda is doing under the hood. So with this ability to have our analysts be able to write SQL code that manipulates this geodata, we are then able to load it all into dbt. And so this is the DAG that we have that generates these tilings in a way that we can access it regularly. What's beautiful about dbt, as I'm sure everybody here is aware, is it's version controlled, it's fault tolerant. And in this case, the incremental and unique indexes feature is super, super important because you can run a tiling on areas that overlap. And we want to make sure that in that final dim tiling table, we don't have duplicates. It's really important that merge goes appropriately. And so dbt's structure lets us really separate out what is, I would call a quite complicated logical process in a way that is like tractable, testable, debuggable, and ultimately makes all of this accessible. And just to help you understand all of this, we're using the classic staging, intermediate, and dimension table design pattern here, where the dim tables are ultimately what we want people consuming for their processes, and the intermediate tables are where a lot of the raw calculation within Snowflake are occurring. Cool. So with all of this stuff available, it lets us combine a ton of data and make a lot of statements. We're a delivery fulfillment company. We can make statements about our orders, the delivery times, what stores there are, what items are available where people are entering addresses, and where should we go into, as well as combine with external data sets. So census data has really nice polygon mapping, and being able to unlock that at a very granular level lets us say, okay, here are these sessions in this area that we don't have any coverage in, and we know the median income and the number of foot, the amount of foot traffic and the amount of area that is roads versus trains and all sorts of stuff like that. Yeah, combined with the total number of sessions there might be, or the total number of stores that might be in that area. So you can imagine that can become very powerful. Okay, I think that is it. Thanks, everybody. And I do want to call out, we're hiring, and come work for us. It's work with us, I should say. It's a great place to be. Thank you all.
That's awesome. Thank you so much, Jake and Athena. I think everyone, there's a lot of like mind blown emojis happening, and we have at least one question. I've got a few, and people seemed enthusiastic about those. I think it might need you to put your slide back up. I'm not sure, but I think the slide where you break down the I think it's the H3 table, just trying to put the pieces together, formulate the right question. With this geospatial data, the right way to formulate it. I don't know if you can go back to the slide that has the chart with the table that has the indexes. Yeah, and maybe give it like, just try to explain it break it down one more time. Absolutely. It was great to have you go back. I just want to give everyone an opportunity to fully grasp that piece of it.
Yeah. Let's see. I think this should be the right. Okay. You can see this again?
We see yeah, we can see it. Yep.
Okay. This one.
Yeah.
Yes. And sorry, can you restate
I know. So
the question?
I think if you're able to just explain this kind of what each of the columns, so H3 like help us understand what the H3 resolution represents and like
Yes.
the number of unique indexes within it?
Yes. Okay, so actually I'm going to go back one more slide.
Okay.
So you see this globe that they have where they've tiled. This is a projection essentially, where they have these hexagons encircling the Earth. Looking at just these very large hexagons, which are like 25% of South America here in the bottom left, that giant hexagon is a single H3 index. And specifically, I'm going to change back to the table real quick before I come back to this globe. That's an H3 index of size 0. So that's an H3 index of size 0. It has an average area because the projection changes depending on where you are. It's not perfectly uniform, but it is approximately uniform depending on how accurate you want to be. That has an area of 4 million square kilometers. And the edge length, so one of the 6 sides of that hexagon, is 1,000 kilometers long. Wow. And there are 122 of them. And with that context, we can go back to this visualization, and we're only looking at a portion of the sphere, but it looks like that count is about right. You would expect, I think, that there are about 100 of these very large hexagons. Now, getting into kind of the lineage stuff I was talking about, underneath it, and hopefully it's visible on your screens here, there are 7 children for those giant size 0 polygons that are also quite large. And so again, looking at that South American central hexagon, those are also large, and they're almost like they're country scale. Mm-hmm. And if we go to that table again and we look, that would be resolution 1. That's 600,000 square kilometers, and there are, 842 of them, and the edges are 400, right? And that same lineage occurs. And so if we go back again, you can see, you're definitely gonna have to zoom for this, you can see even smaller. And that zoom continues to occur. Each of the smallest hexagons on here have millions and millions of children that get very small. I actually haven't even included, so Uber's H3 goes all the way down to resolution of 15. For our purposes at Drizly, that's completely intractable. Like the infra we would need to support it is insane and also unnecessary. We don't need to aggregate at what essentially is, I think it caps out, it's like a little above a square centimeter, I think is the last size. And we don't get GPS that's accurate enough to place within those. And so we don't use that. Where we cap out is at this resolution 9, which is about 1/10 of a square kilometer. And where that's nice is it's really fine grained, but it does allow for sensible aggregation. And so that the hexagons have really nice behavior. You can almost imagine like a chi-square test or something like that, where we are getting above 5 observations in each hexagon.
Thank you so much. That was, you took a poorly formulated question and figured out what I was asking. That was exactly the piece that I know that helped me understand it better. Hopefully same with the group. Okay, so let's see. We've got another question. Mindy, do you want to come off mute and ask your question?
Hey, thanks for presenting. It's really interesting problem space you have and just how you guys solved it. Just wondering, what made you guys choose H3 versus other options like Google S2?
Yeah, great question. We started with Google S2 way back when. A few different considerations came into play. One is S2 has not been updated nearly as regularly. So the community just isn't there. If you look at the project, last I checked in that repo, I think the last commit was 5 years ago. And that's a red flag for me building a system to put something up that nobody's touched. That said, we used a jar built from that for a couple of years, and it was fine. The challenges with S2, while it is hyper performant, like it is a true quad tree in the data structure, which is great, it is irregular. So northern latitudes and southern latitudes have extremely different performance. but it's ripping fast. And if I were engineering a real-time system where latency was absolutely the requirement, I think I would lean towards GeoHash, which is the other system I was going to talk about, or S2, because they have really nice performance properties. H3 has better regularity, which is much better for aggregation. And the functionality of the packages is great. So yeah, that I think is about the entirety of the thinking around that.
Very cool. Okay, we're just timing wise, I just want to be conscious of. But I think one question that a bunch of us are curious about, which I had put in there, is how long did this take to implement? Maybe if you could speak to this, how many teams were involved? How many people? Because we're all just very wowed. And yeah, reminder about the mute. Perfect.
This is a very easy answer if I go the simplified route and say that Jake is a one-man band and basically spearheaded this entire initiative and put together all of the like underlying infrastructure for it, and basically gave the analytics team a like packaged solution where we can just create our own models off of the infrastructure that he put together and then build off of the like baseline in Looker. We did have like team projects where we would add in state level maps so that we could power that in Looker. So we were involved in the process, but I think I would be remiss to not give Jake the credit that he deserves for this, because he really worked hard in terms of timeline. What was it, like a month? You can give me more details there, Jake, but yeah, it was a pretty fast turnaround for something of this magnitude.
Yeah, so once this stack was determined, this was fast. This portion took 2 weeks. The discovery work, which was like soft discovery, not full time, that took months of time. But I think if I could go back in time and be a little more disciplined about how I researched things, I think it is reasonable to do this with an exact same setup as Drizly in the month or 2.
Cool, thank you. There are, if you guys don't mind, there are more questions in Slack. If you want to drop in comments, that'd be awesome. But I want to give enough time for Alex, our next speaker. Awesome.
Right on. Thanks, everybody.
Thank you all.